Good morning, everybody. Today, um, we have the upper last class, and I believe last time we stopped on the let's see, on the data augmentation on the LeNet. S- Um, let's see. Yeah, so we talked about uh, LeNet and um, yes, and I mentioned data augmentation. So I want to show you how to apply data augmentation um, on images. So you will need this for your final project because if you add data augmentation, your accuracy of the classification should increase at least by 5% um, without changing the neural network. So I have uploaded the code. Um, we don't need CUDA. Um, okay. So there is a library which is called Albumentations. If you Google it, you will see the example of kind of image modification. So from one image, you will have here 15 more images. Um, and also you can find here some examples. But I provide this example in the code from last class. So let's upload an image. You remember we upload this in RGB scale. Um, so Argumentation works on NumPy arrays. So um we will read an image in pill library format, then we will convert into NumPy array, apply augmentations, and then transform into tensor format. So that's why we import this uh, to tensor function from argumentation. Argumentation is not defined. So also it complains that I'm using the um, aha. It says that there is another um, function, linear transform, which performs the same, but it's fine. So what do we have here? We can set the because we will crop, we can set the smallest size to consider. Then we also can rotate with some probability. It means that it will rotate in some cases. Oh, wait a second, it's scale. And it won't um, scale and rotate in some cases. Then we crop random patches. Then we change our channels RGB brightness, also with some probability. And finally, as you remember, the pre-trained models, they use their own normalization. So we can also apply uh, normalization and transform to tensor. Um, and then you can apply this my transform in your dataset class. In dataset class, you read an image and you return this image as tensor. But you can return my transform of this image. So it will actually return always the kind of transformed versions of this image. And let's look at some results. Um, so this is the original image, or no? This is after my transform. Okay. Did I divide by 255? Let's double check. I cast to numpy array. So I believe I also should divide by 255. Let's see. Well, actually it works. Um, oh yeah, you can see the result. Every time we apply transformation, it changes the contrast and uh, maybe rotates your image. Um, so the only thing I'm thinking about, when we apply this normalization, we should apply this to image in range 0, 1. So for now, my image, let's double check. Yeah, it's in int8 format, unsigned integer. It's interesting, but it's working. What if we divide this by 255 first? Okay, it looks like this argumentation expects image in unsigned integer 8 format. Okay, so, but at least, yeah, it works. And I add this variance and bias, the mean, just to visualize the image because we normalize this image, and as you remember, to get the image back, we should apply inverse transform. Okay, that's it with argumentation. Let's look at the architectures that you can apply in your project. So uh, in 2010, Stanford University created the competition, which was called ImageNet. And for this competition, they collected about one um, uh, million images. And now those images were much larger, not just 32 by 32 pixels, but 224 by 224, this most image, that's the dimension. And also, instead of 10 classes, like in cifr 10, the task was to classify all the images on 1000 classes. And this was the turning point in computer vision, because people had to create new models that could work with larger images, because we could apply just linear models or small two convolution layers models for MNIST dataset or cifr10. And for larger images, people had to come up with new models. And the next model that won this competition in 2014 was AlexNet, by the name of the creator. And this architecture, as you can see, used very large convolution filters, 11 by 11. So it's 121 times 3, 121 times 3 just for one filter. And after the first convolution, they had 48 channels. So it's 128, 21 times 3 times 48 parameters only for the first layer. And because it was pretty large model for that time, they used two computers for parallel computations. So they used two processors to um, update the weights to calculate the gradient descent. Okay, so but it worked. At the same year, okay, I have also some metrics. So they used radioactivation instead of sigmoid augmentations, dropout, gradient descent with momentum. Do you remember when we talked about optimization? We mentioned gradient descent with inertia, momentum, then adaptive momentum, then adaptive momentum, adaptive gradient, and then adaptive momentum. So, oh, I said 2014, it's 2012. So this Adam didn't exist, wasn't born at that time. So, and the novelty in optimization was gradient descent with inertia. Yeah, they trained for 5 days, and the model had 1 billion parameters. The error was, so the accuracy was 83%, which sounds bad, but because the data set was much larger and images were larger and number of classes was 1,000 instead of 10. So it was the state of the art at that time. In 2014, another architecture won this competition. Um, um, and this architecture was proposed by Visual Geometric Group. And this is the first neural network that has the name of the group, not the name of the authors. VGG. You remember we used last time VGG module. So the main feature of this architecture was that they preserved the shape of the input image. Just add fading. If we add fading, then we can preserve the image. So you can see that we have the input pre-channel image and the shape, which is a standard shape for all these retrained neural networks on ImageNet 224. So when you will do your project, you should also apply the crop. If your image is larger, you should resize and make your image of this shape. So, and then they applied smaller filters, 3 by 3, instead of 11 by 11 like in RxNet, 3 by 3. And so here, after the first convolution, they had 64 channels. The other notes in this paper was that they applied one by one convolutions. One by one convolutions. If you think about your input array, it can be image or just a tensor with some channels. Then we applied convolution and convolution filter, for example, 3 by 3. Look at the neighboring pixels of the corner pixel. One by one convolution will look only on the channels. It won't take into account the pixels around this corner pixel. So it's kind of just linear regression along the channels, because you remember convolution is just weight times the pixel value plus weight times the pixel value. So it's just a linear function, but along, it's kind of mixing the channels. So we used the flatten layer. They applied one by one. Let's look at the metrics. So the advantage of this model was that they used smaller kernels, so they could create more like deeper feature maps with more channels and apply more kernels. Again, gradient descent with momentum, the state-of-the-art optimization algorithm at that time. Drop out the number of parameters. So so 147. This is million. This million. I said on the previous slide billion. It should be million. So At that time, people still cared about initialization because they didn't know wedge normalization. And the accuracy now increased from 83% to 92%. At the same year, the other architecture from Google was proposed with nickname Inception. Google, Google Net, or it's known as Inception because at that time there was a movie with the same name and, yeah, the same title, and in that movie there was a phrase, we should uh, we should go deeper and deeper. And if you look at the architecture, you will understand the connection with that phrase, we should go deeper. So this is the architecture of that neural network, pretty deep for that time. Um, the um, kind of the feature of this neural network was that they used only one-by-one convolutions, only one-by-one convolution. So, and you can understand that for one-by-one convolution, the number of parameters is the same as the number of channels. If we use 3 by 3 convolutions, it will be also times 9, times 3 by 3. So if you use one-by-one convolutions, you can use more convolution filters. Um, the other um, the other note in this model was that they used several outputs from the neural network. Not only the last layer was used in loss function, but also the outputs from intermediate layers. And what do you think? Why they can't just use the output layer and apply classification, the cross-entropy was on the output layer? Why they had to use the outputs from some intermediate layers? What do you think? What was the reason for this kind of using um, values and then applying gradients not only from the last layer but also from the previous layers? Do you remember what was the problem with sigmoid function? So this problem was called vanishing gradients. Even though they didn't, I don't think they used sigmoid function. Um, they they used ReLU, which is a standard activation function for images. But still, because the neural network is pretty long, if your gradient is smaller than 1, and you remember in our gradient calculations in backward, we multiply gradients, like the gradient with respect to the previous layer times the gradient with respect to previous, and so on. If the gradient is smaller than 1 and we multiply it, I don't know how many layers are there, but at least 10 or 20 times, the gradient will be 0. So if we take our output from a shallow layer, so at this layer, we will multiply our gradients less times. So we won't get 0 gradients in when we apply back propagation from the like internal layer. So because if without this additional outputs, this neural network wasn't training because of this gradient, vanishing gradient problem. And we will talk about how to fix this problem when we will talk about next architecture. So for now, the um, characteristics of this neural network one-by-one convolution, more than one outputs in the loss function. So we have like 3 terms in the loss function. Still gradient descent with momentum. And you can see that the number of parameters is smaller than in previous VGG because they use smaller convolutions, even though the network was deeper. And accuracy improved by about 2%. And now we will talk about the architecture, ResNet, residual net, which actually solve the problem of vanishing gradients. So let's in this paper they provided 2 plots when they trained like deeper convolutional neural networks. So this is the training, this is the test. So they trained 20 layers and 56 layers neural networks. And in theory, if our model has more parameters, it should perform better. But in this example, on the test, larger neural network had high error, but also on the training data, the neural network with more parameters also had high error. So it's kind of counterintuitive because we have more parameters, we should learn more from our data. And what do you think? What was the reason for this kind of paradox? Vanishing gradients, because with deeper neural network, there is more chance that multiplication of gradients will vanish. And that's why they proposed so-called residual connection or skip connection. Skip connection is working as follows. So we have one layer in our neural network. Then we have activation. I will skip activation. Then we have another another layer, convolution or linear. So let's call this, for example, X, and this will be f of X. Like the next layer is just a function, activation and linear layer. But instead of passing f of X to the next layer, we will pass f of X plus the values from the previous layer plus X. So we will pass the current value plus the value from the previous. In this case, they skip two previous. So f in this case represents kind of 2 linear layers and activation. Plus X. So let's calculate the derivative. What will be the derivative of x? Yes.
X.
Derivative of x?
X prime.
Yeah. And what is the derivative of x with respect to x? 1, 1. So in any case, our gradient won't be very small because even if the derivative of f will be close to 0, derivative of x will be 1. And this solves the problem with vanishing gradients, because we will multiply the gradients, but now they will be uh, shifted by identity by 1. So this is a very simple idea, but it resulted in very deep architecture. Now we have ResNet 18, ResNet 30, 32 or 34. So ResNet 60, and so you can use 34. You can use a very deep now neural network, and it will work. It will update your weights. So this is the architecture of ResNet. So this is the 2015, next year after um, inception and BGG. And how it works, they keep the image size shape, like in BGG or free blocks. Then they increase the number of channels and um, um, uh, yes, by factor of 2. So there was 64, then the number of channels increases to 128, then to 256, and finally to 512. Then they applied average pooling and fully connected layer. So, and this is the comparison with VGG. That VGG was used much, much less layers. So you could use up to 1,000 layers with this architecture, isn't it? The number of parameters actually was smaller than in BGG, and yeah, and accuracy improved by about 2% on ImageNet dataset. Well, well, the number of parameters, of course, depends on the number of layers. If you use a lot of layers, then you will have more parameters than VGG. Okay, this is it about these architectures. Now let's implement one of architectures, but slightly different, which is called UNet. Okay. So do you have any questions about projects? In project, if you choose the classification project, I ask you just to upload one of the pre-trained models. There is also mobile net, so you can use any pre-trained model from Torch. They were trained on ImageNet, so their last layer is most likely 1,000. Sometimes you will see ResNet 100, so the output number class will be 100. So in your data, I believe you have 50 classes. So what you will need to do, you will need to add extra, it's called head. You could change the head of neural network. Uh, the, for example, the output layer in pre-trained model has the shape 1000. You will need to apply, for example, 2 or 3 linear layers to go from 1000 to your number of classes. And you can apply also dropout in between and batch normalization. And this is uh, the main idea of the project. To get better accuracy, maybe you will need to unfreeze the last 2 or 3 layers in this pre-trained model. You don't need to unfreeze the entire model uh, because it was trained, and you remember it learns features from images. So on shallow layers, it learned the important features for any arbitrary images. So we should unfreeze only the final layers because they were more specific for the data set uh, that this neural network was trained. Well, if you have any questions, just write me email and we can set a Zoom meeting. Okay. The other project on key points on the face maybe it's easier. Well, but then you will need and for that project you will need to write your neural network. So, notebook. Yeah, I want to finish today convolutional neural networks and cover next time the recurrent neural networks. Okay, now let's talk about some applications and very popular application of computer vision convolutional neural networks is semantic segmentation and object detection. What is the difference between semantic segmentation and object detection tasks? Let's upload some data. So for segmentation, we want to label every pixel in our image. For detection, we can just create bounding box like that. So what do you think, which data set is cheaper to create for segmentation or for detection? What easier to label every pixel or just to draw a box? Yeah, you can speak up. Yes. So as you could see from our previous example with ImageNet competition, the data set is very important, very important for um, creating new models, new architectures. But to create a data set, you should spend some money. And this is the data set from Berlin streets. Again, they created this for a competition and they spent tons of money because it takes about 15 minutes to um, label one image, and you can find people who work for $10 per hour. So you can calculate uh, how much money you should spend to annotate thousands of images. Um, so the other difference between segmentation and detection is that in segmentation, we don't distinguish between the objects because we just label people, but we don't care if this is a specific person. It's just a class of people. In case of detection, we can detect the specific, for example, uh, person or the people of specific age, children or adults, and so on. Okay, so they labeled every pixel with colors, like there were different classes, trees, streets, sky, and so on. And we will use a different data set, simpler, just two colors, black and white data set from the car dealership Carvana. And the data set looks as follows. We have um, so the goal is to detect a vehicle, and they created also for competition this data set to create a mask, the labels for the vehicle. And you can see this is the mask, the ground truth. And we want to train a neural network that takes as input an image and returns the mask of the, and you can see how it's uh, um, I don't know, difficult. I think it's difficult to um, make the label these images. So you can see that they also keep the antenna of these tiny details. But in our previous examples, the output from convolution neural network was a classification layer, just a layer with a number of the size of the number of classes. Now, for segmentation task, the output from neural network should be an image. So the output shape should be the same as the input shape. If it's if it was free channel image. In this case, it's one channel, but still the same width and height. And the architecture that returns an image is called UNet because of this U shape. It kind of takes the input image of the large size, then applies convolutions, pooling, which decreases the shape. But then we should upsample again these feature maps to get the tensor of the size of the image. And this is like the default architecture for working with images. If you want to, for example, generate images from text or convert change the style of the images. you will see always UNet architecture in this neural networks. So that's why I want to introduce this UNet, because it's the default architecture for growth with images. So this is the schematic of this architecture. We have the three channel image. Then they crop the center. I don't know, maybe just to avoid some background and boundary effects. And the output shape so if this is 392 by 392, then this region, the central region, also should be 392 by 392. They have the same shape as in the houses. Then they applied pooling. Error stands for pooling, which reduces the shape by factor of 2. Then after convolutions, again they apply pooling, and again they apply pooling. And finally, we get the picture maps of the size 32 by 32, like in our simplest examples from NIST or CIFAR. And here is even 28 by 28. But the number of channels is large. The number of the depth is 124 in this architecture. So after this convolutions and pooling operations, they apply upsampling or up convolution. So last time we talked about, did I mention about interpolation, how to upsample images? So the simplest, so for, let's say we had an image, then we applied the pooling. So from a patch of size 4 by 4, we get just one number if it was max pooling, the greatest value, and the output shape will be twice smaller, and this number will be the first pixel here. Then we apply pooling here, and maybe the greatest value was here. It will be mapped here, and so on. So this is pooling. To upsample, we can use these values and just repeat this value 4 times. So this is the easiest upsampling. So for example, if let's use another color for this pixel, we will just repeat this value 4 times, and so on. We will increase the shape by factor. But this is, of course, this is the easiest upsampling method. Another interpolation, we will use this from a neural network module, interpolate. Works a little slightly differently. It keeps the information about the position of the largest value when we applied max pooling. So it will return this pixel exactly at the same position where it was in the previous before pooling. And then the other values will be just interpolated. It means that they will take the average between these pieces. Another upsampling technique, also you can just use neural network and module dot transpose convolution. I believe it's called transpose convolution. Uh, Transpose convolution actually will it will have learnable parameters, like convolution has a filter with learnable parameters. Transpose convolution also has a filter with uh, some weights, and it will actually learn the upsampling filters. So now we know how to upsample images. We apply upsampling, again convolutions, upsampling, which will increase the shape by a factor of 2, and so on. And finally, we get the output feature, which we compare with our ground truth, like segmentation, for example. So you also can see here these gray areas. These are skipped connection. Skipped connection, the same as in ResNet. We add, so we get so for example, we apply upsampling, but also we add the value from like three layers before. Then we apply upsampling, but also we add the values from 6 or like previous layers. Why did they use these skipped connections? In image processing with neural networks, there is a problem which is
Yes, you seeing if there's any correlation with previous pattern and that.
yes, and especially with
Process one.
and especially with images, especially with original images, because there is a problem which is known as catastrophical forgetting. Catastrophical forgetting. You can see here this works. It was noticed that if we train our neural network, for example, on images of elephants, or if we train this neural network on images of birds, the last layers will be similar for both neural networks. So it means that neural network kind of forgets the input domain. And that's why they use these skip connections kind of to keep information from the input base, somehow to keep the information about our domain of our data. Okay, now let's look at the implementation. So this is kind of dummy implementation of this UNet architecture, but I think it's good just to get the idea. So, convolution block. Convolution block consists of the convolution layer, batch normalization, and activation in my case. So the first layer you can see here, I apply convolution block. I think I'm also using the padding. Yeah, I'm also using padding, so I keep in this example, they didn't keep the size of images. I had padding just to keep the size of images. Um, so it consists, first downsampling block consists of convolution block. Convolution block is it contains convolution, batch normalization, and flash. Another convolution block with more channels. Um, mhm. And the last layer will contain a sigmoid activation function instead of loop, because we will compare with segmentation. This is just pixel values black or white, one or zero. So it's a binary classification for every pixel. That's why uh, I'm using sigmoid, because I will apply BC, binary cross entropy loss. And this is the entire architecture. Um, so we apply this down block with two convolution layers pooling, um, another downsampling pooling, then this middle layer with the small dimensions, uh, middle layer um, contains one by one convolutions, total size one. And then upsampling. Upsampling, and I'm using the simplest one without any learnable parameters interpolate. This is skip connection, concatenation of our current layer out with some layers from the previous steps. In this case, it's a downsampling layer. Upsampling, and again, upsampling it's just convolutions. Again, increase dimension, interpolation. Again, skip connection, concatenation, and out and output of one more interpolation, sorry, and then finally out. So if we train this model with binary cross entropy loss, um, and sometimes for images, it works better RMS root mean square propagation than Arden. So in NLP, typically Arden works better. Um, so I think I can stop training just 12 epochs. So 14 epochs. And let's try to visualize the results. So you can see that even after 13 iterations, 13 batches, sorry, it's not epochs, batches. Our neural network actually provides some segmentation math. But if you continue training, of course, it should provide better segmentation mask. So, do you have any questions about segmentation? If not, the next application is object detection, when we want to create a boundary box. And here, first we will talk about the metric. And you will understand that I spent a lot of time for classification metrics like area under the curve, not just for fun, but because it's used also in computer vision tasks. Of course, it's used in other tasks, but in this case, the main metric for object detection is called, I believe it's called smoothed area under the curve. Let's see. Um, mean average precision. Mhm. And this is connected with area under the curve. But first, let's talk about this metric intersection over union, which is used for object detection. So if you think about the box from ground truth, like green one, and box that your neural network predicted, red one, you should somehow estimate the similarity between these two boxes. And you can calculate the intersection. So intersection in this case will be this region. So what do you think? Do we want a larger intersection value or smaller?
Large intersection value
Larger.
defines the object, in that case, is more defined.
Yes. So let's think about this situation when we have this box detected by neural network, like this box. It will have a large intersection. Actually, intersection will coincide with it will be the maximum intersection as possible. But is a reasonable box that we want to know. So that's why we also take into account the union. Intersection, we want to have greater, and the union, so the union in this case will be the entire box. But the union in this example green, the union will be this region. So this will be the union of these two boxes, and we want to have this union smaller. So this is why the metric intersection over union was introduced, and it looks as follows. Intersection is in numerator, and union is in denominator. So by this value, we can somehow estimate that the predicted box matches the ground truth box. So if we can take some threshold, so if this value is greater than this threshold, then we will call this prediction as true positive, So here is example. If the intersection over union value is, let's say, it's pretty high for a red box, then this red box will be true positive. if the intersection over union is small, uh, uh, then it will be a false positive. It will be a false positive, like here. Uh, so it predicted a box, but this box doesn't coincide with the ground truth. And false negative, will be, for example, if it predicted incorrect class, or um, if our object was actually matched with another boundary box, so we can't detect kind of this object twice. And we don't care about true negatives for this metric, so it's enough just have this true positive, false positive, and false negative to calculate area under the curve, Rock-Auk curve. But instead of calculating area under the curve, um, they calculate actually precision recall curve. As you remember, precision recall curve um, is not monotonous. It can have some jumps. So they smooth this curve, and this is called average precision recall curve. And this value is used as the quality metric, bless you, for object detection. I won't run this code. You can play with that. So what do we want to predict? We want to predict four tuples. The coordinates of the corners, oh, actually, four numbers, just two corners is enough to predict two corners for a box. So we want to predict four numbers. So it's the regression actually task. And let's see, maybe I can even run it, but I also want to talk about Shapley values, like feature importance for images. So yeah, we predict these four numbers upper, if I'm not mistaken, upper left, yeah, upper left corner and down right corner. Here is our metric intersection over union for these two boxes. Um, Here's the example. You can just take one box 0, 2, and the other box 1, 3, and calculate the intersection, which will be 1, and union, which will be 7. And 1/7 should give you this value. Yep. And it's trained. And as the result, we will get some, so white boxes is ground truth and red boxes is our prediction. Let's see. Okay. String just for one epoch. Yeah, and here is the result. Pretty good. Um, let's see. Oh, it's interesting. In ground truth, there is just one box, but definitely there are two people, two persons. And the model actually detects two people. Okay, so this is how the object detection works. Now we have 2 minutes left, and I want to just show you another notebook that I prepared uh, last week. Um, on the feature importance for images. It's called Shapley values. So I think you've heard about Shapley, maybe an algorithm class. So he received Nobel Prize for his algorithm of matching. Okay, I won't go into details. So the idea is that if you think about, for example, street musicians playing on the street, and then they want to decide how to share the money, uh, you can send just one musician from this group and look how much this one person will earn. Then you can send another musician and look how much one the other will earn. Then you can send pairs. Then you can send groups of three. And based on these values, you can finally decide how to split the money. So it's called Shapley values. And if you look at the Shapley values, like pixel importance on images, it's interesting that the most important pixels correspond to the eye area. So that's why if you don't want to be recognized by the street cameras, you should wear sunglasses because more than 90% accuracy of the face pedestrian recognition can be done just for by the eye. So you don't need the entire face at all. So this is how uh, um, I just want to show you how you can calculate the if you will work with security later, you will they actually use this which pixels you can actually change in your image so that the system recognizes your image as a different object. So okay, that's it for today, and yeah, we'll see you next time.